Hello. This week we are going to talk about transistor amplifiers, BJT transistor amplifiers. Of course, amplifiers are circuits that amplify an input signal. So we have, in the case of analog amplifiers, we have an analog signal. We feed it through the amplifier, and what comes out should be a scaled version of that input signal. Of course, a signal is anything out in nature that contains information. Most signals out in nature will be in analog form. Let's say, for example, the speech signal produced by a human speaking. And so that signal contains some information. One of the potential things we need to do with that signal is to amplify it before we continue processing it. And so we have a signal which contains information. We feed it through an amplifier. And what we get at the output is a scaled version of the input signal. Now, we are going to assume that these are linear amplifiers. Now, as we have seen, the BJT transistors and transistors in general, they're not linear devices. However, for amplification applications, we're going to bias them in the linear region of operation. So we can assume linearity. And so we should not be seeing nonlinear type of distortions in our output signals, such as clipping and things like that. It should be really a perfect replica of the input signal. The only thing that should change will be the amplitude and perhaps phase shifts. In our analysis and design of transistor amplifiers, we've already talked about how we're going to split that analysis into the first part, which is going to be bias in the transistor or the DC analysis or design. And the second part is going to deal with the small signal AC amplification. And the reason why we are able to break our analysis or design of transistor circuits this way is precisely because we are assuming these are linear amplifiers, and therefore the superposition principle applies. So for a linear amplifier, we can apply the superposition principle. Which basically says that the overall output of the circuit or of the system is equal to the superposition or the sum of the individual outputs to the different input stimuli. So basically what that means is if I have an amplifier, let's say I feed it with first input X1, and that produces a response output Y1. Then I feed it with a stimulus or input signal X2 that produces an output Y2. Then if this is a linear system, it must also happen that if I apply an input signal which is the sum of the two original input signals, my overall output is the sum or the superposition of the individual outputs. That's how we're able to say, okay, we're going to split all our signals into a DC component and a small signal AC component. And so on the one hand, we handle the DC, and on the other hand, we handle the AC. We first calculate all the DC values in the circuit for the bias point, and then we calculate the AC parameters. And the superposition of the two is going to give us the overall response of the system. Now, there are three basic transistor amplifier configurations that we're going to study. The three basic single transistor amplifiers for a BJT transistor. So basic BJT amplifier configurations. And they follow the names of the three terminals of the BJT transistor. So there is emitter, collector, and base. And the three configurations are called the common emitter, common collector, and common base amplifier. Those are the three single transistor amplifier configurations. The names stem from the terminal where the signal ground is located, or the common ground. That's why the name: common emitter, common collector, common base. A common emitter amplifier uses the emitter terminal as the common terminal. And what that means is that it is common to both input and output. So the structure for a common emitter amplifier will look something like this, where the input is applied to the base of the transistor, the output is taken out of the collector, and then the emitter becomes the common terminal. Common collector amplifier the collector becomes the common terminal. Notice I'm tying it to perhaps a DC source, which for signal purposes, AC signal purposes, will be an AC ground, so a signal ground. The input is applied at the base of the transistor, and the output is taken out of the emitter. And for the common base amplifier, the base is the common terminal, the input is applied to the emitter, and the output is taken out of the collector. So those are the three single transistor amplifiers. And then we're also going to cover how do we connect different stages of these types of amplifiers together to create a multi-stage amplifier, as well as some common multi-transistor configurations, such as the cascode or the Darlington pair. For all these types of amplifiers, we're going to see how we're going to be using them as voltage amplifiers. And the general model for a voltage amplifier, if you recall, so general voltage amplifier model is as follows. It's typically modeled as a voltage source, dependent voltage source, whose value is dependent on some input voltage signal. So multiplied times a gain. So A times V in being the signal applied at the input, and V out being the signal taken at the output. Again, since it's a voltage amplifier, the output voltage is equal to the voltage gain times the input voltage. The typical parameters in any voltage amplifier model will be the voltage gain, which is A, or sometimes we're going to refer to it as A sub V to differentiate it from other types of gains. We have input resistance, R in, and output resistance, R out. Now the gain is the nominal gain of the amplifier. I'm going to write it as A sub V for voltage gain. Is the nominal gain of the amplifier. Typically, if the amplifier is operating under ideal conditions, that should be the scaling factor or the ratio between output and input. The input and output resistances are used to model the interaction of our amplifier with preceding and subsequent stages, and the effect of loading on our amplifier. So basically, the input impedance is, or the input resistance is modeling if we connect an input voltage source, that source is going to have a series resistance, and how is that going to affect how much of the signal, of the input signal, gets transferred to my amplifier. And likewise at the output, I may want to connect a load resistor or I may want to connect any type of load that I model as a load resistance, and the output resistance will tell me how much of a loading effect or a decrease in my effective gain I will get for different values of load resistance. So since this is the general model for a voltage amplifier, and we're going to be studying voltage amplifiers in this chapter, for every single type of amplifier, we're going to be wanting to derive the following: an expression for its voltage gain, an expression for its input resistance, and an expression for their output resistance. Thank you.